Right. Okay, so before we start, I'm gonna explain to you about the uh, the course rencana kuliah ya, or the course lesson here. Let's me this one here. Okay. Okay, so this is the course TK3101 separation processes atau proses pemisahan ya di kelas reguler. We have 3 class, 2 for the regular and the third one is for international, and also will be held simultaneously on Thursday and also tomorrow, yeah, Friday 9 to 11. So let's have a look on the course planning sheet of this chemical engineering for separation process. So it is a mandatory course, the wajib. And then we have 3 credits. So 3 credits means you have 50 minutes times 3 again. So 9 times 50 minutes. So for 50 minutes, or more or less, that would be about 9 hours. Yeah, no, 9 hours per week. So that means you need to spend the time for even for the course, even in the class, in the virtual class, or do the assignments, or to learn this course is up to 9 hours, 8 or 9 hours per week. Okay. So so it is so if we talk about chemical engineering, this third year is very heavy. You will see it, yeah, because you already know the basic in the second year. So in the third year here, you're supposed to start to design some equipment, and then we also in this course there would be number of design project, yeah, design project for per group. Okay. So the prerequisite, we need thermodynamics, chemical engineering thermodynamics, and we also need mass and energy balance. This is the primary references. It's quite old books, because the separation process is actually the quite classical chemical engineering. Okay, so a few years back, when there are ABET accreditation from the USA, one of the reviewer, Professor George, I forgot the name, from Georgia Institute of Technology from the USA. He came to ITB, to chemical engineering, and then see the curriculum, and then and he said that in chemical engineering is a very classical chemical engineering. Okay, so we use quite old book. This is from the Synod and Trable, and also Henley Cedar, but this has been incorporated into the PPT, the presentation that I will give throughout the course. Okay. But if you need to, yeah, but I also encourage you to read this book as the additional books, yeah, even the primary references, yeah. When I was in third year, like you, we always carried out those books, yeah, the Trable book everywhere, because we learn from that. Okay, but now, because you're in the still in synchronic mode, yeah, still in pandemic situation, and you can open in a ebook format. Right, so here we have for K01 is Professor Wanten, Pak Udin, Pak Dr. Hairudin, and also Bu Grace. And then the second class is Professor Danu Aryono and also Bu Anita, Dr. Anita, and for the third class is the me, ya, Dr. Winnie Wulandari. Okay, so just remember your course load per week should be 3 hours for classroom session and 3 hours for tutorial session, and then independent study for 3 hours. So this would be used for your if you want to do assignments or assignment and combination together, maybe around 6 hours per week. Right. So okay, so and then I'm gonna explain to you here about, let me make it smaller here. So in our program, we use outcome-based education. So that means we expect you to know all these things after we give the course. Okay, so after on the completion of the course, the students are expected to be able to explain the fundamental principle of various separation processes. And then we assess that with there would be a module exam, and also there is an oral exam. Okay, we have quite a lot of exam in here because we want to assess them. We want to assess you with different types of assignments, and also to prepare you for the 4th year. Yeah, and then you should be you should be able to calculate the number of stages required for separation. So for example, there would be a distillation and a gas absorption and liquid extraction and leaching. And then also you should be able to determine the height of a continuous pack tower for absorption. So in one of the chapter, we would talk about absorption, gas absorption. And then that, in that gas absorption, there are some calculation, yeah, to determine the height. And then there's also an analytical tools, yeah, how to analyze the range of separation process, and also to how to apply the design into distillation column and pack absorption column. And also we're going to use HISIS as well, very introductory to simulate the separation process. Okay. So for the week by week, in the first week, and also tomorrow, I will explain about the introduction and also the principles of diffusional separations. And then the next week we'll talk about a binary distillation, or what is this distillation. And after that, in the week 5, so you can start to write it now, there would be an exam on distillation. Yeah. And then after that, that would be multi-component distillation and also tri-design column. But for multi-component distillation, there is no exam, but only a group assignment. Okay, because the calculation is quite long and quite heavy. So usually we assign a group assignment to do the work. Yeah. And then we will have a design of a tri-column. Okay, so once you do the calculation by hand, and then for binary only 2 components, and then you learn how about if more than 2 components, 3 or 4 components. And once you know that, and then let's design the tri-column, the tower itself. And this one also a group assignments, and then we will evaluate them with an oral exam, a presentation, and also oral exam, ujian lisan. Yeah. And then so that's all is for the binary, the distillation. And the next one is we go to the module 2, which is absorption or gas absorption. And then there should be some a calculation, and also a packing as well, the designing as well, for pack column. I will explain to you what is the difference between tray and also a pack column later on, yeah? And then there should be one evaluation again, evaluation number 3, which is exam of absorption. Okay, and then and for after this one here, there's also this one, the perancangan. We need to how to, okay. And then after that, there is a liquid extraction, and then we'll have the evaluation 5 at module 3 or UAS, yeah. So, and then if we have per week, you can have additional material such as a leaching or separation with membrane. Okay. Also, for the exam ujian tulis, the exam is if we still follow the last year, the exam is you must pass, or if you don't pass, then you have to repeat it the exam again. Okay, so it's either usually it's either 60 or 1. So here in the exam module 2 or module 1, let's see, in this one, for the module 1, usually there would be there is a 2 question. The first question is the basic question, and the second question is about analytical question, okay, like open-ended question. And then if you can answer the first question correctly, you got 60 points. If you get if you can explain the second question, you got 40, so the total is 100. Okay, however, if you can't if you don't answer correctly the first one, your mark is going to be 1. Okay, and then you have to repeat the number 1 or for the remedial to get the perfect mark. Okay, so this usually there is 1 or 2 ujian perbaikan, yeah, for every evaluation, and then so we'll got to do that. Okay, hopefully you don't need to do the remedial exam, of course, and those remedial exams sometimes will affect the mark, yeah. So if you do 1 remedial exam, then that means your maximum index would be AB, for example. Or if you do 2 or 3 remedial exam, then it should be lower to B, something like that. Okay, but anyway, I don't want you to frighten you a bit, but let's try to do this course together, and then Bu Grace will also help us as well to for the tutorial. So then yeah, so hopefully we can pass those tests together. Yeah. All right, and then yeah, so this is just the course, yeah, the outcome. Okay, now I'm gonna stop it for now, and I would like to invite you if you have any questions regarding the course plan.
I would like to ask a question.
Yeah.
For this course plan, is it accessible for us to see?
Should be. I think I have to put it in EduNext. Is it accessible yet? Not yet, yeah.
I think it's not yet first.
Right.
Yeah, it's not. And second question, where would it be available for us to watch the recording?
Yes, the recording, I will upload it into the EduNext. Yeah. I will upload it into the EduNext. So just wait. I'll just upload it first. Yeah. Let me. So you can try to have a look here. I will upload the recording and then maybe put it into the YouTube because it's quite heavy in the EduNext, and the link will be put into this EduNext. Yeah.
Great, thank you, ma'am.
Okay. Have you have a look about the material in the course plan?
Yes, I have.
Okay. Good.
It's not the course plan yet.
Yeah, so that's the course plan, and then if you look at here, there is an introduction, and then should be here, yeah. Okay, the an introduction here. Wait, let me have a look here, and then there should be some introduction, but still in PPT. So after this, after today, and then after we finish the class, and I will put the video into the YouTube, because it is gonna be heavy if we put the videos all here, and then the link should be available in the Edonex. Okay, so this semester we would like to be much yeah, we will try to put everything on Edonex, yeah, hopefully, yeah. Okay, any other questions? Any other questions? No? All right. Okay, then now let's start opening the slides. So let's wait for that. Okay. Can you see my screen? Hello?
Not yet, ma'am.
Not yet?
Yes, ma'am, not yet.
So let me stop share. How about this one?
We can see it, ma'am.
Okay, good. Right. So we are team teaching. Me, Professor Danu Aryono, Professor Wenton. Pak Ardian now is teaching utility system, I think. This is from last year. And also Bu Ini, and also Pak Khairuddin, and also there's one more, Bu Anita, ya, Dr. Anita, and also Bu Grace. Okay. So okay, so so now you're semester 5, so that means you have chemical reaction engineering 2, yeah, TRK 2, yeah. Do you have it now?
Yes, ma'am.
Yeah, okay.
Yes, ma'am.
So while you learn with Pak Makerti or Pak Haryo or Pak Fadli, yeah, about a reactor in the, let's say, put it with the bracket here, the process. Before we get the feed into the process, we got the reactant into the process. From the initial feed, we have to do some separation. Okay, so for sometimes the feed is they contain impurities, so we have to do a separation to remove the impurities prior to go into the reactor. Okay, and then after we do the reaction, and then in a reactor, and like Pak Makerti explained that, or Bu Melia explained that, yeah, in the reactor, sometimes the product itself, it won't be 100%, yeah. Sometimes there's a maximum conversion, sometimes there is the unreacted reactant will flow outside the process. Okay. So this is also impure. Okay, so, and also if the process comprise of impure gas as the side product, or it release the impure gas, before we release it into the atmosphere, we have also to do separation, so we can separate the contaminant. We have to separate the contaminant before going release to the air. Okay, and then here also there is a clean air, so then we can get the clean air or clean gas that we can release safely into the environment. And while the contaminant, if it can be recycled, then it can be recycled back into the process. And also from the product, because the product is not pure, sometimes it contains the reactant. Again, we have to do a separation itself. Yeah, we have to do separation to separate them into a pure product. Then we can maybe put it into the next unit, into the next processing unit, or maybe for sale, yeah, for this product. And also sometimes in a reaction we can have a byproduct, so we can separate it also with this block separation here to get the byproduct, and this byproduct also can be sellable. Okay, so then we have the remaining reactant. It can be recycled back into the process, or if it is contain wastewater, we can separate it. And then, of course, we need to treat it first before it can be released into the environment, while the contaminant need to be recycled back. Or maybe we have to contain them and then release them in a safe way. Yeah, for example, for the PPLH, or yeah, so it should be stored safely because it's had contamination. Okay, so that means we need a number of separation technology in chemical processes, because in nature there would be always a lot of mixture, yeah, a lot of mixture, even in the gas phase, in the liquid phase, and to be able to separate them into like 100% pure product, we need the technology. Okay. Okay, and then let's see an example of a crude oil fractionation. From 1 barrel of crude oil, 1 barrel is 159 of 59 unprocessed crude oil. It may contains of 60 liter, 70 liter of petrol, 32 liters of diesel, 15 liters of jet fuel, and so on. Yeah. And then so what we need to do with this crude oil is we heat it up with a steam boiler, and then run into crude oil fractionation. Okay, so one of the goals of this course is we want to be able to design fractionation. Of course, it's not for crude oil, it's too complicated, maybe 1 or 2 or 3 separation. So then we can separate them into a top product and also a bottom product. Okay, for this crude fractionation here, we have after the hydrotreating and a cracking unit, we have petrochemical outputs, petrol, kerosene, jet fuel, and so on. Yeah. So this is an example of separation technology. Another one is this one. Let's go back. Yeah, this is a natural gas. So the natural gas, and then oops, let's see. Okay. Okay. So the CO2 separation from natural gas. First we have natural gas, and then the natural gas and then to be shipped, we need to liquefy them. Yeah, if we liquefy the natural gas, the volume will contracted up to 600 times. Yeah, so that means less volume that we need, and then we can carry lots of LNG, right? So the goal is to liquefy this natural gas into LNG. Okay. However, the CO2 contains a lot of carbon dioxide. Yeah, range from 1%, 2%, or in Natuna, like more CO2 compared to the methane. So sorry, I need to go back. Okay, so in the natural gas here, we have to separate the CO2 from natural gas. Why? Because to liquefy the natural gas, we have to cool it down up to minus 100 degrees Celsius, while the CO2 will solidify. Okay, so if we have too much CO2, then it will plug the pipelines, and then it is bad. And so we need to separate the CO2, so the maximum CO2 is up to 200 ppm, or sometimes up to 50 ppm. Then we can safely liquefy those natural gas. Okay, so to separate CO2 from the natural gas, we use absorption column. In a pack column, we also will learn about that in this course, how to separate them, and then how to design the pack column tower. Yeah. Okay. Here another example on the bioenergy field. Okay, so here we have CPO, crude petroleum oil, and it is for a raw material for biodiesel. But before it is used for the raw material for biodiesel, it needs to be treated to become RBD PO, yeah, refined bleach deodorized palm oil. Here there is a degumming, how to separate them from non-organic, from fiber, from water, and then from bleaching to brighten the colors, and also the deodoration to remove the oxidation content in the oil. Okay, so those three steps also comprise of separation technology. So then in the end, we'll get the RBD PO, which is ready for biodiesel raw material. Okay, another one example here, also an example of this one is the reactor to make ammonia. Yeah, so we have the nitrogen and the hydrogen feed gas. Increase the pressure with the compressor. It goes into the reactor here, and then don't forget there is a heat exchanger, and also there's a catalyst. So it's gonna flow to outside here, and then it's preheated with some preheated feed with the gases there, and then it will go through those catalysts at 500 degrees Celsius, and then because the reaction here is okay, let me check. Okay, because the reaction is equilibrium. Yeah. So this is 3, this is that. Okay, because the reaction is equilibrium. Because the reaction is equilibrium, so the output of the reaction, of course, will still contain the unreacted nitrogen and hydrogen. Okay, in the process, we want to maximize the source that we have. We want to maximize the nitrogen and hydrogen reactant. So we have to separate the ammonia from nitrogen and hydrogen. So what we do in the reactor here, we have to follow, we go to the heat exchanger to cool it down a little bit, and then it's cooled down furtherly with some cold water and hot water up to, so this is a type of separation, yeah, where the ammonia in this condition will liquidify, will go into the liquid state, while the nitrogen and the hydrogen still in the gas phase. So the ammonia will flow down there as a liquid, while the nitrogen and hydrogen will go to up there and then go back, and then it's reheated by get the heat from here, and then put it back with the compressor to the reactor. Okay, so with this, they will allow us to get a maximum recovery of maximum utilization of nitrogen and hydrogen. Okay, and then this one, sorry, this one is air separation. Is a membrane technology. Pak Wenton knows a lot about this. Professor Wenton, yeah. So, and also Pak Khairuddin, also Bu Anita, yeah. They are from membrane lab. So here we know that in many chemical plants, we need nitrogen, yeah. We need pure nitrogen. It can be used for utility gas, for instrument gas, or for a blanket gas, or for inert gas. Okay, so one of the technology to use nitrogen or sometimes oxygen is called ASU. Yeah, it's not in the Japanese way, but it is air separation unit. Okay, in air separation unit can be a cryogenic distillation, sometimes can be pressure swing adsorption, or membrane technology. Yeah, so whereas the air is passed through those hollow membrane, and then here which is permeable, and then the oxygen will flow out because of the permeation to the shell there. Well, and then it will leave the pure nitrogen there. All right. Okay. So so that's it. As you see, there is a number of application of separation processes. So our course would be focused on distillation, and then absorption, and then also liquid extraction, and also on some additional membrane separation later, yeah, for the additional. Okay, I'm gonna stop here, and then I would like to invite you if you have questions or comments. Okay, any questions? You're still listening? Hopefully, yeah.
Yes, ma'am, still.
Okay. Do you have a course since morning?
Yes, we do. We have 2 courses previous to
Right.
this one.
Okay. Yeah, me too. Yeah. So this time is quite a little bit sleepy, but I really hope that we still do our best, yes, to deliver the course and also for you to learn. And then maybe later there would be tutorials as well on Thursdays, on 1 hour. So it would be more lively, yeah. Okay, so I'm gonna cut it here. Okay, so this presentation is based on the regular ones. So it's gonna be in modules, yeah. Then I have to go back to the second one. I think this one. Okay, can you see my screen, or is it stop sharing?
Yes, we can still.
Okay. Okay, so now let's go back. Now I'm gonna explain to you about the basics of separation. Is it still black?
No, ma'am.
Okay, let me put it. Okay, how about this one?
Still, we can see the slides.
Okay. Okay, now let's check about the basic separation. Yeah. So this is okay. So let's consider we have a mixture. Okay, so in the previous slides, we understand that. Okay, so we're gonna deal with a lot of mixture, and then we're gonna deal with how we can separate them. So let's think about that. We have a feed. Like a mixture A and B, okay? In a separation, we can't get 100% A and 100% B, okay? Ideally, maybe we can, but realistically, naturally, we can't do that, okay? Just let's say you have a mixture of water and oil, okay? And then and you try your best to separate them, okay? But still, you still have a little bit of water in your oil, and also you still have a little bit of oil in your water, okay? So and also this one here, also for example, we have a mixture of A and B. With the separation process, the product that we have is there would be a product that is rich in A, and then B is very low, or it can be at the impurity. And the second one is maybe the A, which is just the impurity, and the product B. Okay, so it can be separated as A and B, but with still a little bit of impurities. So how much do you want to have the impurities? Of course, it depends on the technology later. Okay, just want to explain that if we want to separate ethane and ethylene, yeah, ethana dan ethylene, ethane and ethylene, to be like 99% of ethane and 99% of ethylene. Sometimes it can requires up to 90 stages, so 90 90 tingkat. Okay, so that is very high, and then so how much degree of the purity of the product, that will determine the technology or the equipment that we will design. Okay. Okay, so yeah, there are two types of mixture. The first one is the heterogeneous mixture, for example, sand and salt. Campuran pasir dan garam, yeah, the mixture of sand and salt. And the second one is homogeneous mixture, or air, for example, how to separate O2 and nitrogen, for example, yeah. For the heterogeneous mixture, we can separate it. It depends. Usually, if we want to separate it based on the size, you can do sieving, pengayakan, or maybe if you want to separate sand and salt, maybe we can selective dissolution, put it into the water, and then have a mixture. And then the salt will dissolve while the sand won't dissolve, and then we can sieve the sand, then we can get the sand. We can get the sand, while the salt, then we can evaporate them, and then we can get a pure salt. Okay, so that's a typical, we call it a physical separation. Okay, but for homogeneous mixture, how to separate it? We can't do that. Okay, we can't do that. So then we're gonna use a diffusional separation, pemisahan diffusional. Okay, in the past, this course separation process, we often call that OPD. Yeah, even maybe some of the lecturers still say it is OPD, operasi pemisahan diffusional. Yeah. During my time in 2005, so it's about 16 years ago. I feel quite old now. we have two course ya, 2 semester. Proses pemisahan 1 dan proses pemisahan 2 ya. But now with this curriculum we only have one process separation. Okay, so let's check. Okay, so what is the diffusional separation process? So the diffusional process, separation process is the separation that use a diffusion as an aid to separate a two phase. Okay, so let's say for example, and first we're gonna use the knowledge of equilibrium. That's why we need thermo, yeah, we need chemical engineering thermodynamics, because we need to know the thermodynamic properties of phases. Let's say we have a mixture, and the mixture in an equilibrium can be separated into two phases, alpha and beta. So if we can separate them into two phases, alpha and beta, then we can separate it. Okay, let's say for example, I want to separate ethanol and acetone, for example. So I'm gonna put it into a two phase where we have a rich phase of alpha and also a liquid phase of beta. Of course, if you have two phase, vapor and liquid, they don't mix together. Okay, so they can be separated then, one for the vapor phase, one for the liquid phase. Okay, we got it for this one, for the phase equilibrium. Okay, so we're gonna use we're gonna bring the mixture into the phase equilibrium. Okay, so then we can get the vapor phase and also the liquid phase, and then we can separate them. Okay. The second one is using the differences in the diffusion rate. Okay, so for example, we have a component A and B, for example, and then this is a permeable or a medium permeable medium, for example. If A is travel faster compared to B, so then in here, A would be much faster passing this medium. So then we're gonna reach maybe more A, okay? And maybe B would be just a little, okay? So the difference in diffusion rate is used for membrane. So in the membrane, they use the property of permeability. So if there is two components, one have a high permeability, easy to pass the membrane, and one of them has a low permeability, is not easy to pass the membrane, then one component would be just easy travel, and then in the other side we have a rich A and maybe small b. Okay, so the use of diffusion, again, we use a phase equilibrium to separate them, or difference in diffusion rate. Okay, okay, so again, so diffusion in phase equilibrium, like I said before, let's say I have a mixture of homogeneous mixture. Let's say I have methanol and ethanol, for example. Yeah, I have methanol and ethanol. I have a mixture of them in the lab. Sometimes you can do it in the do it in the lab tech, yeah, distillation. But we still maybe can't do that because of this pandemic. So it's basically in the module VLE ya, percobaan KUC ya, kesetimbangan uap cair. So we have a mixture of ethanol and water, and then we put separating agent. The separating agent for distillation is if we add energy, yeah, we add heat, yeah, kita panaskan. Okay, so we add the separating agent up to, so this homogeneous mixture can be make it into two phase. Okay. Two phase, phase alpha and phase beta, right? And this phase alpha, of course, in every phase, there is an equilibrium composition. Yeah, you learn in thermodynamics. In one phase, there should be an equilibrium composition. So in the phase A, there would be a rich of A and small b, while in the phase beta would be a B and then with some impurity of A. Okay, and then here, for example, this is the vapor phase and this is the liquid phase, then we can separate together. Okay, so this one here, for example, yeah, so this is, yeah, okay, so this is about the distillation process. So the separating agent is the energy or heat, yeah. So we increase the temperature by adding heat, dipanaskan, yeah. So if, for example, we have a feed in a liquid in a liquid state and then we heat it up, there's a volatility difference between A and B. So volatility or alpha. Alpha is a volatility, which is the ratio of mole fraction of A in the gas in the vapor phase divided by the mole fraction of A in liquid one. Okay, so and then also I define volatility of beta. The B, yeah, the component B, for example, is the mole fraction of B in equilibrium, yeah, in the vapor phase, divided by the mole fraction of B in liquid phase. Okay, so if we have a degree of volatility, for example, this is A. Usually we call it A is more volatile, yeah. If we say some substance is more volatile, that means the volatility is high. So that means at room temperature, it is much easier for the A, yeah, for the component to go into the vapor phase. Okay, so let's say I have a oil, yeah, for example, here. It is more volatile, for example. So that means if I put it, if I open this and then just put it into a piece of plate, for example, after a while it's just volatile, yeah. So that means the volatility is high, and then this goes into the vapor phase easily. Okay, so then if a mixture have a volatility difference between A and B, this one has two different volatility, then we can maybe heat it up, yeah, heat up in some way. So A will go into the vapor phase much easier, while B will still be in the liquid phase. Okay, so once goes to the vapor phase and liquid phase, then we can separate them because it has different phase. Okay, so this is a distillation process. Okay, another example is for gas absorption. Yeah, for example, with the CO2 in the natural gas that I explained before. So if we have a gas dissolve in, or maybe gas, a mixture gas in a G, yeah? Gas S in G, and we have a solubility difference. Solubility means because the gas actually can be soluble in a type of liquid. For example, CO2 can be dissolved in a Coca-Cola, yeah, in a Coke. Okay, so that means if we add absorbing liquid into the mixture of gas, for example, the absorber, for example, usually the absorbing liquid. So for example, this is mixture of CO2 in natural gas. Okay, the CO2 is the gas S, the natural gas is the G. Okay, and then usually we add a separating agent. which is for usually for the absorber is we called it MDEA, monodiethylamine, ya, amine base, NH2 ya, and H2 base, nitrogen base, MDEA solution. Okay, and if we mix them together, CO2 is easier to absorb in the MDEA, while natural gas, it won't absorb by the MDEA. Okay, so the solute, the solute, the G here, would be easier to be absorbed by the liquid phase, while the inert or the G will just stand still in the gas phase. Okay, so then after a while, then the G or the CO2 the CO2 then the CO2 that in the natural gas will be absorbed by the MDEA solution, and then we will release the natural gas, which is clean natural gas with no or very small CO2. Okay. When I have this course, I have a question. So what happened with the liquid phase? Okay, so that's why in the absorption column, the next of the absorption column, there is regeneration tower. So the liquid phase, which is saturated with CO2, yeah, the MDEA, which is saturated CO2, is put into another tower. And then we change the condition, and that condition, the CO2 will be released again safely, yeah, from the MDEA. So then we will have a new fresh MDEA, which is ready for absorbing the CO2 again. Okay, so the process is recycle, where the usually that would be, for example, if this is the tower, we put the CO2 here, CO2 and natural gas, and then it will leave the natural gas, which is clean, and then we have a fresh MDEA, and then the MDEA will contact with the CO2 and then absorb the CO2 in the natural gas, and then it would be full of, we call it pregnant liquor, yeah, full of CO2, and then here they will undergo another regeneration, right? Stripping, or we call it stripping. So then they can get the CO2 out, and MDA can, the fresh pack can go, that one there. Okay, so but in the course we're gonna learn only the absorption, but the stripping is yeah, it's quite similar but different operating temperature. If you think about it, if you have CO2, or if you have Coke, yeah, it feel nice if you have a cold Coke, yeah, because they absorb. So absorption usually held in a low temperature. And the last one, okay, we're almost finished, is the liquid-liquid equilibrium. This is like if we want to, we have tea, let's say we have tea bag, and then the tea is dissolved in hot water, and we want to get the thein, yeah, or the component that makes tea, and then we mix it with organic liquids, okay, and then the tea or the thein, like the caffeine in the coffee, will easier to dissolve in the liquid P, okay, while the water will just stay there. Okay, so then after this, after liquid P, and then we can maybe dry it, and then we can get the tea. So this is called liquid-liquid extraction. Okay, so to sum up, phase equilibrium is a natural process, and the equilibrium composition is a function of pressure and temperature. So we're gonna learn that tomorrow. And then it is based on experiments, and we're gonna learn tomorrow, yeah. And then okay, so I think the times also is up, and then tomorrow we're gonna start from this slide, and I'm gonna tell you more about equilibrium, yeah, vapor liquid equilibrium. All right, there's one last question if you want. No questions? Right then.
Ma'am, do you mind, I'm sorry, I think I missed it from the first course plan. I would like to know if there's a breakdown for the percentage of each exam, how many it would take for the final score.
Right. The breakdown, we usually we normalize it. There's 5 components. Yeah, there's 5 components. Ujian modul distilasi, absorpsi, ekstraksi. Right. There's 3 written exam, and there's 2 oral exam. Tray column, and also absorption column distillation, pack column design. So there's 5, and maybe 1 or 2 quizzes. So there is 7, yeah. And usually this 5 takes account up to 80 to 90%, and then 10% is from assignments and quiz. Okay, but how much? But usually this 3 written is bigger compared to the group assignment. Okay, but the it's just not exact every semester, because we have a look if there's one exam that all of them getting bad at it. Usually we make it smaller, and then we try to get it from the higher marks. Okay. So at least these 5 takes account of about 80% of the mark.
All right, ma'am. Thank you.
Okay, yeah. I'll have a look on the regular classes if they have the mark, yeah, like how much is 85 and so on, and then I'm gonna get back to you tomorrow. Okay. All right, it's almost 3 o'clock, so thank you for your attention, and then I'm gonna wait. Okay, just wait. Maybe tomorrow or sometimes in the weekend I'll sum up and then put it into the EduNext, yeah, so you can have a look. Okay, thank you very much, everyone, and then see you tomorrow.
Thank you, Bu Ini.
Okay.
Thank you, Bu.
Thank you, Bu.
Thank you,
Okay, everyone. So I'm gonna end meeting.